Hello and welcome back. Now what I want to talk to you about today is multi-rail switch mode power supplies. So what is this? Basically it's a type of power supply that has a single input voltage and multiple output voltages. These can be 2 or 3 or however many. So how do you go about building such a thing? One option can look something like this. So you have a single input voltage and you use it to supply multiple independent switch mode power supplies, each having their own switching element, producing the various output voltages. But this is quite cumbersome. I mean, you have lots of little supplies and this just involves a lot of work. Another option you can try looks something like this. Basically you need a single switching power supply and a transformer. So this is of the isolated kind of supplies. And by using a transformer you can get however many windings you want, each supplying whatever voltage you want. This is quite nice, although it involves building this transformer, which can pose problems sometimes. But I want to talk about something different today. What I want to build is a switch mode power supply that has a single switch and no transformer. And using the single switching element is capable of supplying multiple output voltage rails. So let's see how we can build this kind of supply. Now the first thing I want to talk about is the boost voltage multiplier. So to start things off, let's just remember how the boost switch mode power supply looks like and works. So first of all, in the first stage you get energy coming from the input capacitor, which is charged with plus and minus. This charges the inductor through the switch, so you got a certain direction of current going through the inductor. The inductor is working as a load this time, and when the switch opens, voltage on the capacitor stays the same, direction of the current through the inductor stays the same, but this time the inductor turns from a load to a generator, voltage polarity changes, so now you got current going from the input capacitor together with the inductor, going through the diode and charging the output capacitor with a positive voltage in reference to ground. And if we come back to the case in which the switch was on, nothing new happens. So the output capacitor is charged and supplying the output load. So what do we need to do with this to get the voltage multiplier? Well, we need to add a few more components. Basically, we get something like this. So what I did here was take the original boost circuit and add this voltage multiplier stage on top of it. So how does this work? Well, just like before, you get the input voltage charging the inductor in the first stage. The inductor is the load. In the second stage, the inductor becomes a generator. Voltage polarity changes, current direction stays the same, and you end up charging the first capacitor with positive voltage. Now if we come back to the first situation when the switch was closed, now that the capacitor is charged, all the other capacitors are discharged at this point. So we can get current flowing from the first capacitor through the second diode into capacitor C3, leading to it being charged up. Now if you go back to the second situation when the switch opened, now capacitor C3 is charged and we got energy coming through the input capacitor and the inductor, not just through the first diode into the first capacitor, but also through C3 into the second capacitor, leading to C2 also becoming charged up. So how will the voltages look in all of these capacitors? Well, we can say that V1, so the voltage on capacitor C1, is the voltage which we can find in the switching node when the switch is open. So this we will consider the voltage in the switching node minus the voltage on a single diode. So the voltage drop, the forward voltage drop on the diode. And this is the voltage that we'll get into C1. When we come to the voltage on C3, it's charged from the voltage in C1, again minus the voltage drop on a single diode. So it will be the voltage on C1 minus another forward voltage, meaning that this will be the voltage in the switching node when the switch is open, of course, minus 2 forward voltage drops. And finally, we get to the voltage on the output, so V2, the total voltage, which is the voltage on C1 plus the voltage on C2. And this is equal to the voltage in the switching node plus the voltage on C3, so the two voltages added up, minus a voltage drop on a diode. And this will be the total output voltage. So now what can we say about voltage 1 in reference to voltage 2? Well, if we resolve this equation a bit, we can say that the total output voltage is the switching node voltage plus C3, which is again switching node voltage minus two forward voltages minus another forward voltage. So this is 2 V1 minus another diode voltage drop. So in this way, we can get a supply that has higher and higher voltages, and as long as the base voltage is large, then this forward voltage can become neglected. And this is a power supply in which the output voltage will be always larger than the input voltage. The output will have a single polarity, it will always be a positive voltage, and the outputs are non-isolated. What this means is that even if the switch is off, so the power supply is completely off, you will still get voltage on the output. It will not be the voltage that you want, but it will be the input voltage minus some diode drops. So let's see how this supply works using a simulation. So to try things out, I prepared this circuit. The lower half is a boost circuit, and then on top I just got the voltage multiplier stage. So we can see that the first output is boosting, so it's taking 5 volts, turning it into around 11. And then the second output has around 20 volts. So we can see that the second output is 19.9, almost 20 volts. And then the first output is 10.4. So the difference between the two is doubled, minus around 0.8 volts. So that would be the voltage that drops on a diode at higher currents. So talking about currents, let's just see how currents are going through the circuit. So as reference, we can look at the voltage in the switching node. So the voltage in the switching node is high when the switch is off, and then the voltage is low when the switch is on. So when the voltage is high, we can see that we've got current charging our first output capacitor, and then if we look at the other diode, again we see current flowing through this diode also. So when the switch is off and the voltage in the switching node is high, then the two outward facing diodes are charging the capacitors. And when the switch is on, there's nothing going on. Let's just zoom in to see things a bit more clear. Now we can look at what's happening through the other diode, so for diode 7 in this case, and we can see that there's a current spike when the switch turns on, so when the voltage in the switching node becomes very low. Now we're getting a very high current spike because we're using ideal components. So if we just add, let's say, a 1 ohm resistor here, then we can see this current a bit better. So again, we need to reference ourselves to the voltage in the switching node, and we can see that current is flowing through the charging diode, so C8 is being charged when the switch is on. So basically this works just as expected. Now of course we can make a more complicated version of the circuit, so not just double the output voltage, but triple it by adding another voltage multiplier stage. And of course this works as well. So we can see the first output voltage, second output voltage, third output voltage, each being double that of the previous minus whatever voltage drop is occurring on the diodes. And again, if we look at the currents, so we start with what's in the switching node, we can see that currents going to the right to charge the output capacitors are all happening when the voltage in the switching node is high, and then currents going the other way are both happening when the switch turns on, so the voltage in the switching node goes low. So just to make it a bit more clear, I added the 1 ohm resistor, and now we can clearly see that current is going the other way when the voltage in the switching node is low. So this is one way of obtaining a switching supply that has multiple output rails in which you're getting a base voltage and then multiples of that voltage. So the second type of supply I want to talk about is the one in which we take a boost supply, we already talked about that, and add a charge pump to it. And we get something like this. So what we got here, first of all, is the boost power supply, which works like a boost power supply works. So we get our input voltage, charging up the inductor, in the first stage the inductor being a load. No surprise here. Now at the same time, voltage from the switching node doesn't just go to the first capacitor. We get the voltage going from the input capacitor through the inductor down into this capacitor. So it goes through the diode and it charges up our third capacitor. Now if we go back to the first case, the capacitor is charged and we can get current going from the capacitor through the switch, down through the ground, and back through the second output capacitor. So you can get current going through this direction, and what we end up with this time is that the second output capacitor gets charged up with a negative voltage in reference to ground. So what we obtained by doing this is a power supply that has both a positive output voltage and a negative output voltage, or in other words, a differential power supply. So let's just calculate these two voltages. Again, we will be referencing ourselves to the voltage in the switching node when the switching node is open. So in this case, not this one. And we can say that V1 is the voltage in the switching node minus the voltage drop on one diode. Now to calculate the voltage on the second output, first of all, let's calculate the voltage on C3. So this voltage will be equal to the voltage in the switching node minus the voltage on a single diode. So when current goes through this cycle. Now to charge C2, we get voltage from C3 in this case, and again we pass through a diode, so we lose another forward voltage drop. And that means that the voltage in C2 is the voltage in the switching node minus 2 voltage drops on 2 diodes. And of course there's a minus in front because of the way the capacitor has charged. So at the moment, the two voltages are not really equal. I mean, one's positive and one's negative, but that's not what I mean. What I mean is that V1 is larger than the absolute value of V2 by one of these forward voltage drops on a diode. So to get the two output voltages to be exactly the same, we can add a second diode in the path that goes to V1. What this does, it will get V1 equal to the voltage in the switching node minus 2 forward voltage drops on diodes, which will be equal to what we get on V2. So what we managed to create in this case is a power supply in which we have two output voltages, V1 and the absolute value of V2, which are larger than the input voltage. We are getting a differential output, so we get both a positive and a negative output voltage, and V2 is isolated, and V1 is still non-isolated. What this means is that even when the power supply is off, we will still get voltage into the V1 output, not the one that we want, but we will still have something there. But V2 this time is completely isolated because there's a DC blocking capacitor. So when the power supply is off, we have absolutely no voltage in V2 because it cannot pass through C3. So let's see this power supply in a simulation. So in this circuit, we're starting again with the basic boost supply, and I just added on the bottom side the charge pump circuit, so the one to obtain the negative voltage. So if we run this, we can see that we're getting a positive voltage, so higher than the input, turning 5 volts into around 12, 14, and then on the bottom branch, we're getting a negative voltage. So to make the two easier to compare, I'll just change the sign of the bottom one and invert it. Now we can see that the two voltages are close, but there's a bit of a difference between them. So the difference being 12.4 and the other 11.7. So around 0.7 volts, the basic voltage drop on a silicon diode. So again, let's look at how currents are flowing through the circuit. As reference, we'll be looking at the voltage in the switching node again. And we can see that current is flowing through the first diode, charging the initial capacitor, when the switch is off, so the switching node voltage is high. And then current is going through the second diode, charging the output capacitor, when the voltage in the switching node is low. So the two diodes are conducting in either cycle of the switching state. Now another interesting thing we can see is that current through the first capacitor is flowing both ways. So you can see that once we have a positive current showing us the initial charging of the capacitor, and then we have a negative current showing our discharge into the output capacitor. And basically this is how this circuit works. Now as we've seen, the two voltages are not equal, but we can fix that if we add an extra diode in the initial boost circuit. So with this circuit, if we look at the two output voltages, again changing the sign of the negative one just to turn it into positive, we can see that we get almost exactly the same output voltage. So if we zoom in, we do see that there's a difference, but it's less than 50 millivolts. So in most cases this will be good enough. So let's see how else can we improve on this circuit. Now one of the problems with the previous supply was that one output was isolated and the other one wasn't. And to fix that we can build something that works like a dual charge pump. And the circuit looks something like this. Basically what I did here was keep the part of the supply that gave us the negative voltage in the previous circuit and just do some work on the part of the supply that gives us the positive voltage. So the second part of the circuit works just like before. As always, we charge the inductor, and when we open the switch, this charges C3, and then C2 becomes charged. Now, if you come back to the first part of the circuit, when we open the switch, we also have current going from the input capacitor, through the inductor, through C4, and through C1. So basically both of these capacitors get charged at a certain voltage. But if we go back to the first cycle, then we can see that C4 will almost discharge through the diode. So it will not completely discharge, but the voltage on it will remain the same voltage that a diode has forward voltage drop of. So the voltage on C4 will be equal to a diode forward voltage drop. And then when we go back to the second cycle again, the voltage on C4 stays roughly fixed, and all the energy will just go into the output capacitor. Now this is not as efficient as before, so it's not as efficient as a boost supply, but the reason to do something like this is to keep the positive output isolated from the input. So let's just go through the voltages one more time. So we know that the second output voltage is a negative value and is equal to the voltage in the switching node minus 2 forward voltage drops on diodes. So we know this from the previous example. We also know that the voltage on C4 will be equal to the voltage on a diode, so the forward voltage drop on a diode because of this loop that we got going here. And then we can work out that the voltage on C1, so the V1 output voltage, is the voltage in the switching node minus the voltage on C4 minus another diode forward voltage drop. Basically, the voltage on V1 will be the voltage in the switching node minus 2 diode voltage drops. So the two supplies will be equal and we will get the differential supply. So again we have V1 and the absolute value of V2, which are larger than the input voltage. We get the differential supply and we get isolated outputs on both of the rails because of the DC blocking capacitors which are used on both supply rails. So let's see how this thing actually works using a simulation. So here's the circuit, and now the bottom side is just the same as before, so we'll be looking at the top side. So let's see how this behaves. So we got our positive and negative voltage, and if we invert its value, we can see that after a while both of the rails end up giving us almost, well actually there's a very small difference between the two, so this is below 5 millivolts. So the two voltages are pretty accurate. So let's see how the currents are running through this supply. So again we can reference ourselves to the voltage in the switching node, and we can see that current is going forward through the converter when the switching node voltage is high, and then when the switch is on, we're just having current maintained in the isolation capacitor. So we can see that the current through this capacitor is going both ways. So one way when it's charging the output, the other way when the voltage is just being maintained. We can look at the voltage difference on this capacitor. Let's just remove everything else. So you can see that it's always around 700 millivolts. So we're using diode D1 just to stabilize the voltage on this isolation capacitor. So this is just used as a buffer between the input stage and the output stage. And this way we can obtain complete isolation between the two outputs and the input. So the ground is still common, but the outputs are completely isolated when the power supply is off. Now, these are some very interesting power supply concepts, but are they practical? I mean, other than for demonstrative purposes and showing nice simulations, are they ever used? Well, I came across this datasheet. So this is from Linear Technologies, which is owned by Analog now, and it's for a small little switching supply. So here we have a typical application for it. It's a supply with integrated transistors and other things. So what I want to show you is not really this supply in particular or its datasheet. I mean, it's a good datasheet, but that's not the point. What I want to show you is in the second half of the datasheet, and these are some typical applications for this. So it's a boost supply, and here we have a boost converter for it. Then we have a C-peak converter application and another boost converter application, and then it gets interesting. So one of the applications presented here is this differential or dual output converter where the outputs are disconnected. And they're also using this resistor trick to limit the currents going through the switch and the diodes. Then we have a triple output voltage supply in which a plus minus 9 volt supply is being produced, and then a plus 18 volt. So they're using a voltage doubler, the standard boost, and then the charge pump type of supply for getting the inverted voltage. And then they're using again a triple voltage supply with a voltage tripler this time, and then the same boost and negative voltage supply. So if you want to build an TFT LCD bias supply like they are building here, or maybe you just need a differential output voltage for whatever circuit you're building, maybe it's an amplifier or something, then this sort of supply can be quite useful. So what other kind of power supplies can you build with multiple output rails that I haven't covered until now? Well, while doing research for this video, I came across this document. So this is a very nice document explaining how the CHUK, SEPIC and Zeta converters work, and then it also mentions a new converter. So the author calls it the X converter, so pretty cool name, and it covers a lot of mathematics about how it works, and well, it's pretty interesting. So if you like this sort of documents, then go ahead, check it out. I'll be leaving a link in the description, of course. And finally, the author gives this application. So basically, what we have here is an example of differential output power supply. On one side built with the CPIC and CHUK converter, and on the other side built with the Zeta and X converter. So what's special about these? Well, they have DC isolating capacitors, so when the power supplies are off, the outputs are completely disconnected from the input. And since these are second order converters, the output can be both higher or lower than the input. So with all of the previous supplies I showed you, the output was always higher than the input. With these, it can be either higher or lower. Now, I don't want to go into too many details about how these supplies work. The document covers this quite thoroughly. Let's just see them operating in a simulation. So I got both type of supplies right here in the same simulation. So on the left hand side I've got the CPIC CHUK pair, and on the right hand side I've got the X Zeta pair. So let's run the simulation, see what happens. So we can see that the CPIC is giving us a positive voltage and the CHUK a negative voltage, and on the right side the Zeta is giving us a positive voltage and the X converter a negative voltage. And all the values are pretty similar. So if I just invert all of the voltages which are negative at the moment, we can see that almost all of these end up at roughly the same value. So if I simulate for a longer period of time, to give the converter more time to stabilize to reach steady state, we can look at the output voltages, and now all of them are almost exactly at the same voltage. So whether it's a positive or negative power supply, all of these are giving us the same output voltage. Now another thing we can observe is that on the left hand side we've got a series inductor and a low side switch, and on the right side we've got a series switch and a low side inductor. Now the left side is producing positive voltage spikes and the right side negative voltage spikes. And we can see that the converters themselves, so the C-peak and choke, are almost exactly the same as the X and theta, the only difference being that the diodes are pointing in opposite directions. Basically, these supplies work with different types of input voltages. On one side we work with positive voltages, on the other side we work with negative voltages. So that's where the difference in the first part of the power stage comes from. And just to show off that these supplies can make both lower than the input voltage, so at the moment all of the voltages we looked at were larger than the input voltage. So we got 5 volts on the input and around 18 on the output. Now by playing with the duty cycle, making it lower than 50%, the output becomes lower than the input. So here on the bottom side I've got the same supplies, only the duty cycle has been reduced. And this time the absolute value of all of the voltages is below 5 volts. So this sort of supply can either be used to give an output voltage which is higher or lower than the input voltage, or you can use it to give a stable output voltage even if the input voltage is higher or lower than what you're trying to obtain. And well, that's about it from my side for today. So hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and hope to see you next time. Bye bye.